Hi, today I'll be talking about last-iterate convergence rates for min-max optimization. This is joint work with Jake Abernethy at Georgia Tech and Andre Wibisono at Yale. I'll start by giving a short introduction to min-max problems. In classic min-max optimization, we have an objective G that takes two inputs x and y. The goal is to find an x star y star such that the inequalities shown hold, namely that changing x star will not decrease the value of G when y star is fixed, and likewise changing y star will not increase the value of G when x star is fixed. This pair x star y star is called a min-max, or also a Nash equilibrium. Min-max optimization is a well-studied problem with applications in many different areas, such as constrained optimization, robust optimization, and game theory. Much classic work in min-max optimization was focused on the case when G is convex in x and concave in y. In this case, one can find a min-max by updating x and y iteratively with no-regret algorithms. For example, one can use gradient descent for x and gradient ascent for y to get a method known as gradient descent ascent, which we will abbreviate as GDA. The time-averaged iterates of x and y will then converge to a min-max. The averaging in this method crucially relies on G to be convex-concave. In recent years, there's been increased interest in nonconvex-nonconcave min-max optimization. One major application is to generative adversarial networks, also known as GANs. GANs use a two-player game to train a neural network to produce samples that are close to some target distribution. Often this is used to produce synthetic images, such as these images of fake celebrities on the right. Training again amounts to finding a min-max for a certain non-convex-nonconcave objective shown here. When G is non-convex-nonconcave, the classic average-iterate convergence proofs no longer hold. The non-convexity means that averaging doesn't help from a theoretical perspective. Instead of taking the average iterates of an algorithm, one can instead use the last iterate of an algorithm and try to prove last-iterate convergence guarantees. For instance, gradient descent ascent is still popular for applications such as GANs, but instead of taking the average iterate, the last iterate of the algorithm is often used in practice. In this talk, we will focus on last-iterate convergence guarantees for convex-concave problems. Algorithms with last-iterate guarantees in the convex-concave setting will more readily transfer to non-convex-nonconcave settings because they don't have an averaging step that would depend on convexity. As we will see, many algorithms that converge in the average-iterate sense actually do not exhibit last-iterate convergence. For example, using the last-iterate of gradient descent ascent leads to issues with training GANs such as non-convergence and cycling. It turns out that even in simple cases, one can see that GDA doesn't have last-iterate convergence. These animations show an example where the last iterate of GDA cycles outwards, even though the average iterate converges. Moreover, this isn't just an isolated phenomenon. Murdochopoulos et al. Prove that all fall-the-regularized leader algorithms provably do not have last-iterate convergence for a broad class of min-max problems. That means that we need to use new algorithms to find last-iterate guarantees. So why doesn't gradient descent ascent converge? We can look at the simple case of an unconstrained bilinear objective where G equals the inner product of x and y. We also write the update of GDA here. Due to the form of the objective, we can rewrite the update like so. And from the update in this form, we can see that the gradient descent ascent dynamic moves in a circular trajectory around the origin. Let us now define a quantity h as the squared norm of the gradient. A simple calculation shows that the update of GDA is orthogonal to the gradient of h. Another way of stating this is that the dynamic will move tangent to the level curves of the norm of the gradient of G. Since the min-max of G occurs where the norm of the gradient is 0, then gradient descent ascent will not make progress. This quantity h was called the Hamiltonian in Balduzzi et al. 2018. Note that the Hamiltonian is minimized when the gradient is 0, so if we minimize the Hamiltonian, we will find a critical point of G for the unconstrained setting. If all critical points of G are min-maxes, as in this example, then we will have found a min-max. This motivates the Hamiltonian gradient descent algorithm. Which is gradient descent on the Hamiltonian. We abbreviate Hamiltonian gradient descent as HGD. In the picture from before, where GDA moves along the red arrow, HGD moves in the direction of the orange arrow. This algorithm was mentioned in Mescheder et al. And Balduzzi et al., but they did not prove convergence rates. HGD is a second-order algorithm, but it can be implemented in terms of Hessian vector products, which are as fast as gradient updates in applications such as neural networks. Note also that if G is sufficiently smooth, then H is also smooth. Here we see another picture of where GDA cycles outwards while HGD moves directly from the starting point towards the min-max. As mentioned before, no convergence rates were previously proven for HGD. One obstacle is that the Hamiltonian may be non-convex, so we may get stuck at a local minimum of H, which will not be a min-max of G. Our main result in this paper is to prove the first convergence rates for HGD. In particular, we show that HGD converges at a linear rate for a class of problems we call sufficiently bilinear. A representative example of such a problem is shown here, where F and H are L-smooth and convex. Note that even though there is no strong convexity here, HGD still converges at a linear rate. Our analysis also allows us to prove convergence rates for the related consensus optimization algorithm of Mescheder et al. There's been some recent work done on last-iterate convergence. A number of results show linear convergence where the objective is strongly convex or linear in each variable. More recently, Azizian et al. And Liu give linear rates for other algorithms in similar settings to ours. Finally, Golowich et al. Show last-iterate convergence of the extra gradient algorithm for smooth convex-concave problems. So these aren't linear rates, but they are in a much more general setting. In our work, we proved the first last-iterate convergence rates for the Hamiltonian Gradient Descent algorithm using some different methods compared to other work. Here we show a more precise statement of our results. We first define bounds in the eigenvalues of the second derivatives of G. In particular, we define upper and lower bounds on the eigenvalues of the squared blocks of the Hessian, as well as upper and lower bounds on the singular values of the off-diagonal block of the Hessian. L here represents the smoothness of G with respect to x or with respect to y. Rho and mu represent the strong convexity of G with respect to x and the strong concavity with respect to y. We allow rho and mu to be 0, which corresponds to the case where G is not strongly convex with respect to x or strongly concave with respect to y. Lowercase and uppercase gamma represent bounds on the singular values of the off-diagonal blocks of the Hessian. Using these bounds, we can write the sufficiently bilinear condition shown in red. If G is not strongly convex in x or strongly concave in y, then rho and mu will be 0, so the positive term is simply lowercase gamma to the fourth. This must be larger than L squared times uppercase gamma squared for the sufficiently bilinear condition to hold. So essentially, the smallest singular values of the off-diagonal block of the Hessian must be sufficiently large compared to the largest singular values of that block and compared with the smoothness of G. The name sufficiently bilinear is motivated by the fact that adding a sufficiently large and well-conditioned bilinear term to an objective will allow it to satisfy this condition. Note that for the bilinear case, when G is the inner product of x and y, we have that L is 0, so this condition holds. To prove our results, we show that the Hamiltonian satisfies the PL condition in certain settings. This then implies that HGD converges linearly to its global minimum as long as the Hamiltonian is smooth. Proving that the PL condition holds involves proving several linear algebraic lemmas relating to the second derivatives of G. We'll conclude by briefly discussing the consensus optimization algorithm of Mescheder et al., which essentially combines the HGD update with the gradient descent ascent update, which we denote as psi here. For notational convenience, we let Z denote a pair of iterates x, y. Consensus optimization uses the parameter gamma to control the weight between these two updates. Mescheder et al. Show that consensus optimization can be used to train GANs effectively in practice. And using our results for HGD, one can prove linear convergence rates for consensus optimization as well when gamma is sufficiently large. To recap, we proved last-iterate convergence rates for Hamiltonian gradient descent for sufficiently bilinear problems. Our proofs involve showing that the Hamiltonian satisfies the PL condition for certain min-max problems. Hamiltonian gradient descent is a natural algorithm for min-max problems, and understanding it more fully allows us to prove convergence rates for related algorithms such as consensus optimization. Thank you.